This is Physical Chemistry. Part 3. Quantum Chemistry. Chapter 23. The Chemical Bonding in Diatomic Molecules. Section 23.1. Generating Molecular Orbitals from Atomic Orbitals. The exact wave function of a molecule that consists of M nuclei and N electrons can be written in this form. This is a wave function of N electrons and M nuclei. The lowercase r is the position of the electrons. The uppercase r is the position of the nucleus. So we have N electrons, we have M nuclei. Each r, no matter lowercase or uppercase, is a three-dimensional vector that specifies a position in the x, y, z Cartesian coordinates. For example, this r1 is a vector, and this lowercase r1 is the sum of x1 times the unit vector in the x direction plus y1 times the unit vector in the y direction plus z1 times the unit vector in the z direction. The Bourne-Oppenheimer approximation allows us to separate the motion of the electrons from the motion of the nuclei. Mathematically, it's this. The total wave function of all electrons and all nuclei can be written as the product of a wave function of electrons and a wave function of the nuclei. So there's two wave functions. This one is a function of the electrons. This one is a wave function of the nuclei. Over here in this function, although it looks like a function of all electrons, we still need to know the positions of the nuclei to determine the attraction between the electrons and the nuclei. However, in this case, the positions of the nuclei are fixed. Therefore, we consider this function as a function of electrons only. The Bourne-Oppenheimer approximation is based on the fact that electrons move much faster than the nuclei. So, if the nuclei change their positions, the electrons can change their positions immediately and fast enough that there's no effect on calculating the attraction between the electrons and the nuclei. And this is the reason why we can separate the motion of the nuclei from the motion of the electron. Similarly, the motion of the sun can be separated from the motion of the earth, which allows us to focus and calculate the orbital motion of the earth without worrying about the motion of the sun. So again, the sun moves, but at the same time, the earth moves correspondingly. And that's why we can focus on the orbiting motion of the earth. So now let's remove the kinetic energy terms of the nuclei. And then the total energy operator becomes this. This is the Bourne-Oppenheimer Hamiltonian. You have the kinetic energy of all electrons. You have the attraction terms. Pay attention to this negative Z sub A here. Attraction is negative. Z sub A is the number of protons in nucleus A. This is the electron-electron repulsion. Pay attention to this J is greater than I condition. J should not be equal to I because that would result the self-repulsion of an electron, and that's unphysical. An electron does not repel itself, so J cannot be equal to I. And the reason I put J is greater than I here is to avoid double counting of the repulsion terms. That means if we write 1 over R12, that's the repulsion between electron 1 and electron 2. Then we should not include 1 over R21 as well, because 1 over R21 is also the repulsion between electron 1 and electron 2. So by enforcing this J is greater than I, we avoid double counting the repulsion terms. You can also replace this J is greater than I with J is different from I. If you do that, you need to add a 1/2 coefficient in front of the sum sign to avoid double counting. Over here, this is the repulsion between the nuclei. For the same reason, we specify this inequality. B has to be greater than A to avoid double counting of the repulsion between the nuclei. For a molecular structure with fixed nuclear positions, this part can be easily calculated. So we know the number of protons in each nucleus, and because the nuclear positions are fixed, the distance between the nuclei is a constant. So this part can be easily calculated, and it can be separated from the electronic energy. For example, if we calculate the total energy of water, if we know the positions of the oxygen and hydrogen nuclear positions, we can easily calculate this repulsion terms between the three nuclei. And then we just need to use the Schrodinger equation that contains these three terms to solve for the electronic energy. And then finally, we sum up the electronic energy and the repulsion between the nuclei. We get this Bourne Oppenheimer energy of the system. So this is the electronic Hamiltonian. It is the Bourne Oppenheimer Hamiltonian minus the repulsion between the nuclei. So this is the expression of the electronic Hamiltonian. We have the kinetic energy of all electrons. We have the attraction between the electrons and the nuclei. We have the repulsion between the electrons. And over here, this is the Schrodinger equation. And I should replace this BO with ELEC, because we're just talking about the wave function of the electrons. Fortunately, we do not have to use a quantum mechanical wave function to describe the nuclei. So in this sense, the electronic wave function is the same as the Bourne Oppenheimer wave function. Our goal is to solve this equation to get the energy of the electrons. That is electronic energy, assuming the positions of the nuclei are fixed. And then we can include the repulsion between the nuclei. All right, so it's right here. So this is the repulsion between the nuclei. And then we sum up the electronic energy and the repulsion between the nuclei, and then we'll get the total energy of the system, excluding the kinetic energy of the nuclei. And finally, we will learn later in statistical thermodynamics how to calculate the kinetic energy of the nuclei at a given temperature T. So really, we'll be able to calculate the translational energy, rotational energy, and vibration energy of this nuclei in a molecule at a given temperature after learning statistical thermodynamics. To solve for the electronic energy, we need to construct trial functions for the electronic wave function. Why is that? This is because once we have more than two particles, and a molecule does include two particles, we'll have to make approximations. One reasonable approximation can be made using the LCAO-MO method. What is LCAO-MO? This is a theory that states that the molecular orbitals in a molecule can be written as a linear combination of the atomic orbitals on the individual atoms in this molecule. For example, if you have a H2 molecule, the molecular orbitals in H2 can be expressed as this. You are looking at the linear combination of two atomic orbitals. This one is the 1s atomic orbital centered on nucleus A, and over here you have 1s atomic orbital centered on nucleus B. Ca and Cb are the molecular orbital coefficients. They're numbers. They can be real numbers, they can be complex numbers. In this class, we try to use real MO coefficients to simplify the situation. Again, this phi sub H1SA and phi sub 1 H1SB are the atomic orbitals centered on the hydrogen nucleus A and hydrogen nucleus B.